Alright, before I start on intermolecular forces, one thing I wanted to go over that I was looking over that I didn't remember going over was how to calculate out the molar mass of an acid. If they give you a problem that looks like this, they say a student dissolves 1.65 grams of acid in distilled water and then titrates it. They titrate it using 88.43 milliliters of 1.102 molar NaOH. They want to know what the molar mass of the acid is. The molar mass of the acid, to find it, is very simple. You take the grams of the acid that you're given, goes on top, and you divide by moles of the acid. Well, grams of the acid is simply right here, the 1.625. So I take on the top, I get 1.625 grams, goes on top. The only other thing I need is the moles. And remember, whenever you do a titration, at the end of the titration, moles of the acid is equal to moles of the base. So they give me the molarity and the volume of the base. So if I take molarity times liters, I get moles of the base, which at equivalence is also equal to moles of the acid. So I'm going to take the 88.43, change it to 0.08843 times, it's supposed to be a 3, times the 0.102. When I multiply those two numbers together, that's going to give me the number of moles of the base, but also moles of the acid. So then what I do when I multiply the two of them, I take the 0.102 times the value of 0.08843 here, I get 0.00902 moles. I'm going to drop that down here where moles of the acid goes, 0.00902 moles. Divide one and the other, and I get 180. With sig figs, I put 180 point. And that is the molar mass of the acid. So it's very simple. Grams of the acid is given to you in the problem. Moles of the acid comes from the titration because moles of the base is equal to moles of the acid at equivalence. Whenever anything is titrated to equivalence. Alright, intermolecular forces. You guys are asking questions about that. Remember, the key thing is intermolecular forces involve a pure substance. So the word solution does never appear. They're two separate ones. I'll do intermolecular forces first, then we'll talk about solutions. The key thing with intermolecular forces is how sticky the molecules are. There's different things that make them sticky, but how do we tell in chemistry how sticky they are is by looking at their physical properties. So first of all, the greater the intermolecular forces means that we'll have the stickier molecules mean they're harder to separate, so it'll have a higher boiling point. That'll also have a higher melting point. Then the only one that goes the opposite is vapor pressure. So this is for IMF of a pure substance. So that's when we talk about intermolecular forces. So for example, if you look here, they talk about two things. Solubility. They talk about permitidine, which is soluble in water, and benzene, which is not soluble. So the first thing you have to do is classify the intermolecular forces. Well, if you look here, if we go to our chart, actually, intermolecular forces, there's three kinds. The first kind of intermolecular force is hydrogen bonding. In order to have a hydrogen bond, you have to have fun. Hydrogen directly bonded to a fluorine, oxygen, or nitrogen. Dipole. Dipole means the molecule is polar, and when we talked about Lewis bonding, you should know that a polar molecule has either a lone pair of electrons on the central atom, different terminal atoms, or is only made of two. The weakest out of all the IMF forces is London. London is basically, in anything that's non-polar, is automatically going to have London forces like noble gases, and that's based on the greater London forces. First and foremost is based on the number of electrons. We can infer that by molar mass. The other thing that separates out London forces is the more elongated a molecule is, the greater the London forces. These two things right here are what we call polarizability. That's what the term something is polarizability. The more electrons something has, the easier it is to polarize, or the longer the molecule is, the easier it is to polarize. So we come back to this problem right here. Benzene only contains carbon and hydrogen, means that this molecule is nonpolar. If it is a nonpolar molecule, it means the only force this thing has is London forces. Pyrimidine here, if you notice, zoom in right there, you have the nitrogen with the lone pairs of electrons is going to make this molecule polar. We should know from taking chemistry that water is a polar molecule. And remember, substances that are polar dissolve in substances that are polar a lot easier. Therefore, this is more soluble because this one's polar, and this is less soluble because that one's nonpolar. We go back to our chart. Remember, IMF is the weakest force. Ionic is always stronger. And then finally, network covalent are the strongest forces. Typical examples they use on the AP test are SOI2 or diamonds, represent network covalent forces. Ionic compounds, the way we tell the difference between their forces, first is by charge of the ion. If the charge of the ion is the same, the way we separate them out is by their strength or stickiness, is by the size of the ion. The smaller the ion, the stronger it is. So let's take a look at some problems. Look right here. They show you two molecules. The normal boiling point of the ether is 250. The normal boiling point of this one, they say, is 351. This one is stickier. Why? It has a higher boiling point. It goes back to the idea. Something that has a higher boiling point automatically has higher intermolecular forces. So we go back and look at the problem. Well, what do we see? If we look here, I see hydrogen bonding. So there's two forces in the ethanol molecule. Hydrogen bonding, because the H is directly bonded to the oxygen, and it also, anything that's made of nonmetals contains London forces. Now we look at the ether. Why is this less sticky? Well, the ether's predominant force right there is that. The lone pairs of electrons on the oxygen make that molecule polar. So when we look at the ranking system, dipole is here. Dipole is here. Hydrogen bonding's here. That's what makes ethanol a stickier molecule, is because of the hydrogen bonding. This one is a polar molecule. It's less sticky. They tell you SO2 melts at 201. SiO2 melts at 1800 Kelvin. What's the difference in the boiling points? We have to first discuss their forces. SO2, bunch of nonmetals put together, is held together by intermolecular forces. We just say this is just regular IMF. So this is regular IMF. I can't write it, but it's right there. SiO2, if you notice, it's one of the examples they use on the AP exam of network covalent. So when we go to identify the forces, we say SO2 is intermolecular forces. If you draw it out, there's a lone pair of electrons. So it has dipole forces. SO2 is network covalent. So you talk about the forces in each, and then this one melts at a higher temperature because network covalent bonds are stronger. That's all you have to say. Then they say the normal boiling point of Cl2 is higher than the normal boiling point of HCl. Count for the difference based on the types of intermolecular forces. If you look in this case, this one only has London forces. That's all this has. So that has London forces. But its molar mass is 71 grams. HCl is a dipole molecule, so it has dipole forces. But the molar mass of this is only about 36.5 grams. Since this value, they're asking you to explain why 238 versus 188. Normally when we rank, anything that is dipole always ranks ahead of London, normally. But if you have a situation where the molar mass is doubled, this has so many more electrons, we would say this is more, wait for it, the magic word, polarizable. I think that's how you spell whatever. I'm not an English teacher. Anyway, so that one becomes more polarizable. That's how you'd explain that. Here's another typical IMF question. They tell you NH3, CH4 have similar molar masses. Why does NH3 have a higher boiling point than CH4? It's more sticky. Look at the difference in the values. We come back to the table here. Let me clean this up. We come back to the table here, and what do I notice? Well, I know that NH3 has the fun rule, has hydrogen bonding. CH4 exhibits London forces. So when you're asking to explain, the first thing you would say is NH3 has hydrogen bonding and London forces, because any non-metal, any compound made of non-metals is going to have London forces. The only thing CH4 has is London forces. In this question, make sure you discuss both substances. Next thing they ask is ethane, C2H6 versus hexane. If you look here, ethane is a gas, hexane is a liquid. First, you have to talk about the forces. All they have, if it just contains carbon and hydrogen, is London. They both just have London forces. So ethane, you would state, has London. Hexane has London. The difference is this one has more electrons. The fact that it has more electrons means that it's more polarizable. You could even talk about the fact that it's elongated also, because it's a 6-carbon chain. It has greater London forces, therefore we know liquids have greater intermolecular forces than gases. Because remember, solids have the most intermolecular forces. They're held together really tightly. Liquids have a little less, and then gases have the least. So that explains the difference between the gas and the liquid. SiO melts at a higher Si melts at a higher temperature than chlorine. Why is this so much more sticky? If you have a nonmetal that melts at a high temperature, the only thing that's going to explain it is the fact that it must be network covalent. If they give you something you've never seen, but it's a nonmetal with a very high melting point, all you have to state is that it must be bonded network covalently. Last one. MgO is a metal and a nonmetal that is held together by ionic forces. NaF is held together by ionic forces. Why does MgO have such a higher melting temperature or melting point than NaF? Well, let's look back at the ionic compounds. First thing that distinguishes ionic compounds is charge. Is there a difference between the charge? We go back and look. Mg is 2 plus, O is 2 minus, therefore it has a much higher charge versus Na, which has a charge of +1, and fluorine, which has a charge of -1. Therefore, what explains it is you could say the lattice energy is a good term to use, or you could just say the ions are held together by a stronger attraction. Greater the charge, the stronger the attraction. Let's take a look at another intermolecular force problem. This one. First, describe the forces in each. F2 is a gas. We know that has less IMF. I2 is a solid. Explain. Well, if you look at both of these are held together with just London forces. Neither one are polar. If they're diatomic molecules, they couldn't be polar. It's the same atom bonded to each other, so they both have London forces. So what explains the difference? Well, this one, I, has much more electrons. We can tell the number of electrons by molar mass, but don't say because of a molar mass. But because it has more electrons, we use the magic word, it's more polarizable. Next substance, when you go and look at compare the next two substances. If I look here, I have NaF, which is an ionic compound, a metal and a nonmetal. CsCl is an ionic compound, which is a metal and a nonmetal. Why is this one stickier or have greater forces? Well, if we look, the first step we always look at an ionic compound is charge. See if there's a difference in charge. So we come back here, Na is +1, F is -1, Cs is +1, Cl is -1. So there's no difference in charge. So it has to be size. So the second thing is size of the ion. The smaller the ion, like little magnets, the stronger the attraction. So we go back here. Na and F are very small compared to Cs, which is very far down in the periodic table. Because if you look periodic table, remember, as you go towards the corner, the atomic radius gets larger and larger. So you basically say that these NaF, these two ions are smaller, therefore they have a greater attraction than Cs and Cl. And then you get that from just looking at the periodic table. Here's one last one, same thing you've seen before. NH3 and NF3. This one, because of the H, contains hydrogen bonding. Has a higher boiling point, 240 versus 144. They both have London forces. This one is a dipole. If you drew out NF3, you get N. That's what NF3 looks like. The dipole goes a lone pair of electrons. This has hydrogen bonding, so therefore they both have London, This one has hydrogen bonding. This one has dipole. And that's how we would account for the difference in the boiling point. If you look here, ionic compound, ionic compound. This one boils at a higher temperature. First thing you look at is charge. K is +1, Cl is -1, and A is +1, Cl is -1. So it can't be charge. So if you look, the first points you get for is identifying them both as ionic. You want to state both, because remember how they always highlight all substances. Students have a tendency to leave that out. How would I account for the difference in melting point? If there's no difference in charge, it's got to be size. Na and Cl are much smaller atoms than K and Cl. Well, actually, Cl is the same size in both of them. So then how do we account for the fact, if you look on the periodic table, sodium is higher on the periodic table than potassium is, which means it's smaller. Therefore, greater attraction means it's stickier, which means it has a higher melting point. We reviewed this before. This is more atomic structure, but remember, ionization energy is related to the smaller the atom, the harder it is to remove the outside electron, which is ionization energy. So when they ask typical questions, they'll give you a table of ionization energies. They'll usually tell you where it is in the periodic table. First three ionizations for 4 elements in the third period of the periodic table. So which element is the most metallic in character? What does metallic mean? Metallic means that it is very large and likes to lose electrons very easily. So if you're very large and you like to lose electrons very easily, that's going to be element 1. I'm sorry, I lied. That's going to be element 2, because element 2 has the largest or the smallest ionization energy, which makes it easier to remove. Which means if the ionization energy is small, it's an inverse relationship. It means the size of the atom or atomic cloud is larger. The next thing they ask you to do is they ask you to identify element 3 and explain your reasoning. Well, if you look, let's see here. The first 3 ionization energies, let's see. I should have a periodic table in front of me, actually. So if I look here,